Hello everyone, uh, I am Fauzi from Physics Department. Now I would like to introduce the idea of two-dimensional Ising model. That will be the project for multi-core lecture by Ibrahim Safran Hoja. So let's get started. Here's the outline. So in this presentation, first of all, we will meet with Ising model, what is Ising model, and some basic property of it, and then we move to the statistical physics. I will introduce to you the fundamental physics behind it, and then the algorithm. That maybe we will focus more on this, and then the reference of the presentation. So let's talk about the Ising model. So what is Ising model? Ising model actually is a mathematical model for studying fast transition of magnetic matter, proposed by Ernst Ising in 1925. Ising proposed the model as his doctoral dissertation. Back then, Ising only worked on one dimension Ising model. So Ising built the model which consists of spins that can be in up +1 or down -1 states in an L times L lattice. This is the basic construction of the model, and each spin can interact with each other, and if all the spins align in the same direction, then we have magnetic material or ferromagnetic. The other case is paramagnetic. Just for your information. And in fact, as temperature increase in everyday material, of course, we can see that the material will lose their magnetic behavior, and the magnetic behavior lose at what we call the Curie temperature. The value is around 2.269185, at least the previous value that I can give. And it was firstly solved analytically by Onsager in 1944. So Onsager is actually Ising supervisor. Okay, Onsager solved the model for the two-dimension Ising model, and it becomes the most successful model, which we will focus on it in this project. So in short, Ising model is a process for solving statistical problem numerically by using Monte Carlo method. Okay, so Monte Carlo is process of generating random number. In this random number here is the spin, represent the spin that we will place in every side in the lattice. Okay, the more general version of the Heisenberg of the Ising is a Heisenberg model, where Ising is only the special case of it. And if you want to learn more about this, you can implement the Ising model for other things like social interaction, how people interact with each other, and also economic market, how to maybe predict the future of economy of the state, or maybe more actual case like virus spreading, and many more, I believe. Okay, so let's get focused on what we will do. As you can see here, this is the representation of the Ising model, Ising lattice. So the left hand you can see the ferromagnetic material of the model. The right hand side is the paramagnetic material or non-magnetic material. The left one side you have the spin line in the same direction, so the sum of it will give you magnetic material, but the right hand side you have a little bit different kind of spins here, and it produces paramagnetic, since the summation of the spin down spin up here will produce 0. Okay, this is only the simple example, but you can have as many LEDs as you want. Okay, so here we enter some physical term, the energy Hamiltonian. So generally the Ising model have the following Hamiltonian, the equation 1. What is Hamiltonian is, if you may ask? Hamiltonian actually represent the energy of the system. If you know the energy of the system, then you can produce other physical quantities of the system. Here for Ising, you have two terms. The left one side represent the interaction between spins, like spin I to spin G. You have two interacting spin here with their coupling constant G, and the coupling constant may produce positive or negative value according to the spin lines. So if you have two spin up or two spin down, then you have positive G, so the sign here does not change. But instead, if you have different kind of spin, like spin up, spin down, and spin down and spin up, then the G will be negative and the overall sign of the left term here will be positive. Okay, the right hand side here, the second term in the right hand side represent the effect of external magnetic field H on spin I. So instead of the interaction between them, they can also be an external field that affect the system, and of course it can change the energy of the system. This basic idea of the Ising model, and this is how we define the neighborhood of our site. So let's say we have spin at point I here, and for neighbors we define it to have 4 neighborhoods, which means that the spin in point I can only interact to the right, up, left, or its bottom side. And for the boundary condition, we use the periodic one. Periodic mean, for example, if you have one here, the one side, and then the left neighbor of side 1 is 6, and the upper neighbor of side 1 is 31, and so on. This is the basic idea to define the neighborhood of each site in our project. And we move to the physical quantity. So every site here we will scan for each site I to the n, and it's the number of total site in our system, and it represents the magnetization per particle. And also we have the magnetic susceptibility and internal energy per particle, and also the specific heat of the particle. All of this quantity can be produced from our model. So we will computationally solve the Ising model, the two-dimensional, and then hope to produce all this quantity. And those theory can be converted to more numerical variables. For example, the magnetization will be defined as this, as equation 6 shows. And then the value of magnetization, the mk here, is computed in the case for K1, which represent the spin configuration of the system, or we may say S1. Okay, so we can have m number of spin configuration. So each configuration is a set of values for the n spin variables. Okay, you will compute all the sites here. Okay, and by the effect of interaction, spin in each site can change its direction, like up or down. We call this flipping procedure, and the flipping procedure will be generated according to this probability configuration of the spin k, for example, as this, where z here represent the partition function. Partition function is so powerful in statistical mechanics. If you know the partition function, then you can generate every physical quantity that you want from the system. Note here that beta represent the temperature, so we will have a random unit of the temperature, and random in here we use free parameter, free units, you know. So beta represent the temperature, as you can see later in the program. Here I give you some results that have been done. I actually only copied from Toral books for the case of 400 square sites. The first one here, the A picture, represent the Ising model for temperature 4, and the B represent the behavior of the system at the critical temperature. And for more lowest temperature, you have picture C here, and then even more lower you have picture D. So you can think that the dark side has spin down and the bright side has spin up. So as the temperature decrease, you can see the material becomes magnetized. So from A, the higher temperature, it becomes clustered in the critical temperature, and then for more lower temperature, the magnetic behavior becomes more real, you know. I mean, the material becomes magnetic material, ferromagnetic material. I think it's clear what we will do in our project, and this is what I mentioned before about the physical quantity that we try to produce for different kind of lattice. For example, is given here. The upper left represent the energy for temperature. This is the magnetic susceptibility according to temperature. This is also the energy versus temperature, and this is the specific heat. Sorry, maybe it should be M here. Yeah, this is M. Sorry. Okay, and we can produce as many lattice as we want, and it's clear here the behavior of the physical parameter in the critical temperature. Okay, I think you don't really interest about what is the physical thing behind that, but this is what the physicists, especially one who learn the statistical mechanics, focus on. Okay, and this is the maybe part that you've been waiting for. Okay, so this is the algorithm that we will implement. So first of all, we will generate the configuration of the Ising randomly. So here we will produce L time L lattice, and then compute the initial energy. After that, determining interval for temperature. Here we will maybe define from higher temperature to lowest temperature, and then after the initial configuration ready, then we will move to perform the flipping process according to Metropolis algorithm. So Metropolis algorithm is the most general procedure, general Monte Carlo procedure for running the two-dimensional Ising model. So the idea is that if the energy decrease, then flip the spin. Okay, the energy of the spin decrease here, but if the energy is increased, then we need to check is that in the range of the probability. Okay, it will be more clear if you see the C++ code, I believe. And here we give a little bit implementation of Wolf algorithm to make the computation more efficiently in near the critical temperature. Okay, Wolf algorithm from the literature that is implementing in near the critical to see the behavior more efficiently. So the spin will be counted clusterly, not spin by spin. Okay, and then we repeat the procedure to approach physical system that we want. As you know, physical property of material it has a big number. I mean, to get the physical property of the material, we need a big number. Maybe you remember the Avogadro's number. It's like 10 to the 23. So you can define lattice 10 to the 23 and do the calculation, run the calculation. And this is the reason why I choose the Ising model for our course, since I believe by using the parallel computing procedure we can make the implementation, the compilation of the code maybe more faster than the normal computer can. I think that is the idea. If you are interested about it, you can check Raoul Torrell and their code books. And for the C++, I directly get it from Victor 7 code. You can check from his GitHub site. And for more about the Ising model, you can try see Martin here. I believe Martin and Squareman have the Python Python type of this Ising model. Okay, maybe I can give you a little bit tour about our program. So here is the Ising C++. I will send it to Ibrahim Hoja, so I hope he can give to the one who interests to this project. Okay, after defining some basic variable, we move to call the functions. Okay, you can see it later. I just give you a little bit tour here. Here is the main function. We generate all the random number here by using this library, Merson Twister, special library for C++. And this is the temperature for maximum value, and this is the minimum that we'll implement. You can change it if you want, of course. And for the purpose of Wolf algorithm, we define the upper and lower temperature for near the critical temperature, as what Onsager had predicted before. You can see in the previous presentation. And for more detailed one, you can check it out by yourself. Okay, and after the main function, we will define all the functions that will be called in the main function. I think that is for me. I hope you can understand it. If you are not, then maybe we can communicate more further using email. You can take it from the presentation, I believe. Okay, yeah, you can contact me here if you want. So I think that is for me. I hope you understand it, and have a nice day.